Hello everyone. In this particular lecture, we are going to discuss about velocity analysis. As we know, we have discussed the various types of mechanisms. In the velocity analysis, we'll be finding the velocity of various points in a mechanism, and from finding the velocity at the various points in a mechanism, we can find the acceleration of various points in a mechanism, and thereby we can find the force that is acting on the mechanism. As far as this course is concerned, we'll be discussing about the methods to draw or to find the velocity of various points in a mechanism, and also finding the acceleration of various points in a mechanism. There are two methods of finding the velocity and acceleration of various points in a mechanism. That is, one is the analytical method and the second one is the graphical method. Analytical method involves certain equations. There are various methods like vector method, like algebraic method, etc. Some of the method, that is vector method, we have already, or you have already studied in engineering mechanics course in the dynamics part. In this particular lecture, we are going to concentrate on the graphical method. There are two types of graphical methods to find the velocity of a point in a mechanism. One is known as the relative velocity method, and the other one is known as the instantaneous center method. So first we are going to discuss about the relative velocity method, and thereafter we'll be discussing about the instantaneous center method. Since we are discussing about graphical method, you would require the drawing instruments. So here in graphical method, we will be making drawings as per the given dimension. So you must be having a pencil, scale, a rubber, protractor, set square, compass, etc. This is a prerequisite for studying this method. In the relative velocity method, we take each link of a mechanism at a time. We find the velocity of a point on the link with respect to or relative to another point on the same link. And based on the velocity that we get, we make a velocity diagram, which is a vector diagram. Once we find the velocity of a point in a link relative to the point in the same link, we move on to the next link. So that is the procedure in this method. The first link that we consider for the analysis is the driving link. Or in other words, we can say that we first consider the driving link for analysis, and then we will move on to the other links. And as far as the motion of each link is concerned, there are various types of motions we have seen for a link in a mechanism. They are rotational motion, translational motion, or a combination of rotation and translation, that is general planar motion. But for the relative velocity method, we assume that the links in a mechanism always undergo a rotational motion about a point on the link. That is the assumption based on which we do or we follow the relative velocity method. Due to this, you must have an understanding about certain concepts that you have learned in engineering mechanics dynamics part, that is related to the velocity and acceleration analysis of a body or a particle which undergoes rotational motion. If we consider a particle let P be the particle which undergoes a rotational motion. Let it be a circular motion. We assume that the particle, that is P, is rotating in the anti-clockwise direction. Since the particle is undergoing a rotational motion, if you consider the velocity of the particle, let V be the magnitude of the velocity of particle P. As we know, velocity is a vector quantity. It has got both magnitude and direction. We assume that the magnitude of velocity of particle P be small v. What will be the direction of the velocity? We know that when a particle undergoes a circular motion or a curvilinear motion, the direction of velocity of that particle will be tangential to the path taken by the particle at that point. Understood? So that tangential direction, let us assume that it is taken by a unit vector which is known as ET vector. Okay? So this ET vector, ET unit vector is a unit vector which indicates the tangential direction of the particle. So when the particle moves or it has traveled a small distance, let's say the particle has reached this particular point, let the point be P prime. Okay, in that case the tangential direction or the direction of ET unit vector will be tangential to the curve at point P prime. So this will be the direction of ET vector when the particle is at P prime. So you must understand that the unit vector, that is the tangent, which indicates the tangential direction, always changes with respect to time. Okay? So right now we will come back to the initial state, that is the particle is at P. The velocity or the magnitude of the velocity of particle be V. So then how will you indicate the velocity vector? So the velocity vector can be represented as the product of magnitude and direction. We know that the magnitude of velocity is small v and the direction of the velocity of particle at P is indicated by the unit vector ET. So this equation represents the velocity of particle which is undergoing a circular motion. That is V equal to magnitude into direction. and the direction of the particle will be along the tangential direction. Okay, so when you consider a particle undergoing rotational motion, the direction of its velocity will be always tangential to the curve at that point. Okay, so this understanding is very important. When we discuss about the acceleration part, I'll be telling you about the acceleration of a particle undergoing curvilinear motion or circular motion. Right now, please understand this concept, that is velocity. When a particle undergoes a circular motion, the direction of the velocity of that particle will be tangential to the curve at that particular point, and the velocity will have only the tangential component. And this equation can be modified, that is the magnitude can be modified. We know that v can be modified as, small v can be modified as r into omega, where r is the radius of the circular path and omega is the angular velocity. Okay, now this particular concept we will be trying to place it in the case of the velocity analysis for a mechanism. Okay, so this concept we are going to introduce it to a link. So here we are going to consider a link OA which undergoes a rotational motion about O, which is the fixed point in the link. The link is rotating in the anti-clockwise direction with an angular velocity of omega. So we are going to consider, or we are going to find the velocity of point A relative to O, which is the fixed point. So when you are asked to find the velocity of point A relative to O, you must find the magnitude of the velocity and the direction of the velocity. Now, so the previous concept, or how to bring the previous concept here? We know that the link is undergoing a rotational motion about O. So we can consider A to be a particle which undergoes circular motion about O, right? So when the particle A is at that particular instant, what will be the magnitude of the velocity? Or we can write velocity vector A relative to O can be written as V into ET, right? That is what we have learned, where ET is the unit vector indicating the tangential direction. So this will be the tangential direction. This will be the tangential direction of velocity at that instant, right? So this equation can be modified. That is, magnitude V can be written as magnitude V equal to R omega, where omega is the angular velocity of the particle A, which is nothing but the angular velocity of link OA. So omega can be written as angular velocity of link AO. and r is the radius of the circular path. So here what is the radius of the circular path? It is nothing but the length of the link OA. So this equation can be modified as V equal to the magnitude of the velocity equal to OA into omega AO. Okay, so this can be OA or AO. So to avoid confusion, I am going to write it as capital AO itself. Okay, so the velocity of point A relative to O is equal to, or the magnitude of velocity of point A relative to O equal to AO into omega AO, where AO is the length of the link and omega is the angular velocity of the link. So this is the magnitude of the velocity of A relative to O. What about the direction? The direction will be tangential to the circular path. Okay? Tangential to the circular path at that particular instant. Or in other way, tangential is nothing but perpendicular to link OA. Okay? So the direction will be perpendicular to link OA. The direction of velocity of A relative to O will be perpendicular to link OA. Since in this case the link is rotating in the anti-clockwise direction, the direction of the linear velocity of A relative to O will be towards the left side. If the motion was in the clockwise direction, then the direction would have been the opposite. Okay? So this is how we find the velocity of, or the relative velocity of, or velocity of A relative to O. That is, we need to find the magnitude and direction of velocity. Okay? Now, this magnitude and direction, we need to represent it graphically. Okay? So that is what we are going to see now. So we have found out the magnitude and direction of velocity of A relative to O. Now that we are going to introduce or show it graphically. To show graphically, first we need to locate the fixed point in the link. The fixed point in the link is O. So some space, okay, some location, you just mark point O. The O should be small letter O. So first we are going to indicate the direction of velocity. We know that the direction of velocity is perpendicular to link OA towards left. So this is the direction of velocity of A relative to O. So what you do is, first you have to draw a line perpendicular to link OA. Okay? Okay? And then you have to draw a line parallel to this line. Okay? From O. Okay? And since this is the direction of velocity, you have to draw a line parallel to this line from O towards left. Okay? Towards left. And what is the length of this line? What is the length of this line? The length of this line will be the magnitude of the velocity. That is, the length of the line will be OA into omega OA. That is the magnitude of the velocity of A relative to O. That will be the length of the line. So if you, for example, if you get the length as 5, if the magnitude of velocity is 5 meter per second, so then the length of the line should be 5 units. Okay, it can be millimeter, centimeter, anything, but it should be 5 units. Okay, the end point of this line will be small a. Okay, so the length OA is the magnitude of velocity of velocity of A relative to O. Okay, so this is the idea. So once we consider one link, once we finish drawing the velocity diagram of one link, we will proceed to the next link. Okay, so using this concept, we'll be doing the other problems. So this is one of the problem, that is where we consider a slider crank mechanism. The dimension of the crank is the dimension of the various links in a slider crank mechanism is given. So before starting to do the velocity analysis, first you need to draw this mechanism. The dimension is given. So based on the dimension, with the exact dimension, you have to draw this mechanism first, and then we will start drawing the velocity diagram. Okay, so when you start drawing, you take a fresh page in your notebook and try to orient the notebook horizontally, and at the top, you draw this mechanism. So this diagram is known as the space diagram, and this space diagram should be drawn with exact dimension. You can scale it. Okay, you can increase the dimension, increase the scale or decrease the scale. That depends upon you. But the diagram should be drawn with exact dimension. Okay. So this question, you please note down. We'll be doing the problem in the next class, in the next video. Okay. Then after that, we'll be discussing about this particular problem where it is a 4-bar mechanism. The 4-bar mechanism, we'll be trying to find or do the velocity analysis. Okay.